Morning, folks. Let's go and get started. So we'll just sort of review all the stuff that we've had for the exam, which will be on Monday. Sort of the take-home that you're doing is worth 15 points, so there'll be 85 points on that exam. And you'll have fewer multiple choice. I think I put 10 multiple choice on there, so they'll count fewer than they usually do. I think 15 or 20 points they count, and then you're going to have 5 or 6 free response questions. Okay. As I told you before, especially for chapter 6 and 7, I'm going to stick really closely to the homework. Make sure that you get all the homework. They're not going to be identical to the homework, but you'll want to stick closely to that. Also, make sure that you're aware of what's on your equation sheet. We'll look at that. I'll sort of review, summarize all those different circuits that we've been dealing with. But if you know your equation sheet, you should be pretty good because the equation sheet has a lot of information on it. With chapter 5, I'm just going to sort of go through and summarize, not in great detail, but just summarize all the different topics that we're doing. With chapter 5, we have the force on a current carrying wire, IL cross B. We did this before. You could see another cross product, but we had cross products on our last test, but you could see this as well. We did an example problem like this. That was one where you had a wire that had a current going through it, and you had to find the X and Y components of L. If you look back in the notes, we did a quick test like this, and I think there's a homework question like it as well, and then doing this cross product. Okay. Also, you need to know generators and motors. How to apply the right-hand rule in these cases and how they work. That is, if I, like that problem where I had a spinning coil of wire or a current running through a wire with a magnetic field, what's the direction of the force, that sort of thing. And then also just sort of in general how they work. Maybe in a couple of sentences, I could ask you, how does this work? I'm not saying this on the test, I'm just, just sort of running through. I've done that in the past. Need to know your mass spectrometer, how it works. Remember, we developed this equation for the radius. It's I think it was mv over qb. This is on your equation sheet. In a mass spectrometer, you measure the radius for a given speed of your particle and your magnetic field, and then you can calculate the mass to charge ratio, and then from a set of known particles you can figure out what was your unknown particle by the mass to charge ratio. We worked one like that in class. They're an old test, what have you. You need to know the magnetic field due to a long straight wire. In fact, let's just sort of review the right-hand rule. We had right-hand rule for now 2 scenarios. The right-hand rule for a wire in a magnetic field. This was just like what we had with a free particle in a magnetic field, but here we let our finger go in the direction of I, magnetic field is into the page, so in this case our force would be up. This is B, this is I in the wire, and then we also had another right-hand rule where if I have a wire with a current going through it, what does the magnetic field do to that wire? I let my thumb go in the direction of the current, like this, and then my fingers wrap around the wire and give me the direction of the magnetic field. So in this case, my magnetic field will be into the page on this side and out of the page on this side. If I have another wire, say going in this direction, my magnetic field will be into the page on this side, out of the page on that side. So in the middle, my net magnetic field would be into the page. If they were going the same direction, the net magnetic field is out of the page. So, is 0. If this wire is going in this direction, then this wire would produce a magnetic field that would be out of the page, and the two would cancel out. That's our other application of the right-hand rule. You also need to know this application right here with the solenoid. Remember, with the solenoid, it looks like this. If I look at it from the top, say my solenoid looks like this. If I have a current going through it like this, the magnetic field in the middle, in this case, thumb in the direction of I, into the page, out of the page. So in this case, in the solenoid, my magnetic field would look like that coming out of the page. So those are our applications of the right-hand rule for that part. Also, of course, you need to know that for the cross product as well, to do your I cross J, J cross K, K cross I business. All right, that's it for chapter 5. Chapter 6 and 7, I want to just start with, so for chapter 6, our big thing was magnetic flux and Faraday's law. We said that the EMF is equal to minus N d phi dt. That is, the EMF that's induced is dependent upon the changing magnetic flux. And then you also need to calculate the magnetic flux, where phi is equal to the integral of E dot dA, excuse me, not E dot dA, B dot dA. All right, we've done this before. In practice, if your area and your magnetic field are in the same direction, that way, and your area does not depend upon the magnetic field, or vice versa, the magnetic field does not depend upon the area, you can take that P out, and then it's just doing the integral of dA, which is just the area of your circle. So if it's a circle, it's pi r squared. If it's a square, it's that sort of business. We had a couple of homework problems, and we did some in class that were like that. I would expect to see something like this for sure on the test, where I give you some function for B, how it changes. We did this in the homework, and then I ask you what is the induced EMF. There were a couple of variations in the homework and in the questions we did in class on that, so make sure you look at those, and you'll certainly see one of those on the test. Okay, that's Faraday's law. Also, we had some conceptual questions. If you go to the website, I put up the chapter 6 on the concept test. They have the answers and the questions. Just go through them and make sure that you're clear on what happens with these. You might see some of these verbatim. Is that me, BP? The projector, or is that somebody else? Okay, it's not the projector though. Okay, make sure you go through this. You'll probably see a couple of these questions in the multiple choice. They might be verbatim, they might be a little bit different. Let's see. Lenz's law, make sure you're up on that. We had some questions both in class, and this is Faraday's law, by the way. Lenz's law, remember we used to find the direction of the induced current, and it just said that this is to find the direction of the induced current. We had a couple of rules that we gave in class, and I would expect to see some questions where I just ask you, what is the direction of the induced current? Remember, Lenz's law talks about how the induced magnetic field will oppose a change in the flux. So you need to ask yourself the question, what is the direction of the changing flux, and is it increasing or decreasing? That also comes up in these problems here. You can go back and review those problems that we did in class or in the homework. You need to know the direction of the induced EMF in order to answer the question properly. Okay, so Lenz's law comes up in that. Use it to determine the direction of the induced current or the direction of the induced magnetic field. Those are really the same thing, because the induced current produces the induced B field. Then we got into our circuits, our inductance circuits. We had 3 different circuits. We had RL circuits. RL circuits, remember, if we plot I versus T, it looks like this. That's for when you turn it on, when you first turn it on. When you turn it off, I versus T looks like this. Be able to, for all of these circuits, be able to graph out the current or the charge or the energy versus time. So for the RL circuit, they're just like RC circuits. They work mathematically just like RC circuits. You have those exponential functions. The time constants are all very similar. That is, they are fully on, if you will. That is, that they reach their maximum or their minimum current after 10 tau, our time constant, just like for RC circuits. So these work identically to RC circuits mathematically anyway, but the physics behind them is different. We also had, there are some homework problems on this. Make sure that you know how to calculate the current at a particular time. Look at those homework closely. That'll be very similar to what you have on the test. Then we also did LC circuits, an inductor and a capacitor. So that looks like a circuit that had just an inductor and a capacitor. And remember, with these, we had the charge, or excuse me, the energy oscillated back and forth. So we plotted, say, the energy of the magnetic field that's in the inductor, and then also the energy of the make sure we get this right. No, I should go the other way. The energy of the electric field that's in the capacitor. This is in the inductor. Make sure that you understand how those energies trade back and forth. Again, there's homework problem 2 where you have to find the current at a particular time in the circuit, or the charge on the capacitor at a particular time. Let's take a look at those equation sheets. You'll have this entire equation sheet on the upcoming test. Give me just a second to stop there. Okay, so like here's our LR circuit. This is the current as it's turned on. This is the function that looks like this, I versus T. The thing that's not here is what happens when the current is decaying, when it looks like this, but that's just going to be E over R times e to the minus t over tau, just like we had with capacitors. So you just drop the 1. This is a growth function, this is a decay function. Exponential growth versus exponential decay. This is our LC circuit. This describes how the current oscillates back and forth. So my current, let's see, sine is 0. It starts like this. My current goes back and forth at this frequency. Remember, something that's not written here is that omega is equal to 2 pi f. That's not on the equation sheet, so you just need to know that. But that's in general true. So if I give you a frequency, which I will on the test, you will need to convert it to an angular frequency. All right, this is frequency, 60 hertz or whatever it is, like for our power supply at 60 hertz. This is angular frequency, which you'll need for that cosine or sine function. Is that clear? That's not on there, but you'll need to know that the angular frequency is 2 pi times the frequency. We saw that last semester. That's why it's not on the equation sheet. So that's our LC circuit. For the damped RLC circuit, remember this is the one that looks like this, where it is an exponential decay function overlaid upon a trigonometric function, an oscillating function. Be able to calculate the charge at any particular time. That's this. In these cases, we'll assume that phi is equal to 0, so that's our phase constant. So just be able to calculate that. Also be able to describe how this graph looks. That it's an oscillating function, it's a cosine function actually, overlaid upon an exponential decay. Yeah.
Are all RLC circuits damped?
Are all RLC circuits?
Yeah, like are all.
Mm-hmm. All RLC circuits are damped. Because what is the damping mechanism in an RLC circuit? The resistor, right? A resistor is a damping mechanism because it takes energy away from the circuit. So they're damped because they have a resistor. It's just like the LC circuit, but then you start taking away energy. So U degrades over time. Okay, you're not going to see any of these 3 circuits where it's just a resistor, capacitor, and inductor. But you could possibly see an RLC circuit. There's a homework question. If you see an RLC circuit, it'll be a lot like that homework question. Just basic stuff about asking what is the current or the charge at particular times in that RLC circuit. Okay? You could also see phasors. You will see phasors, in fact, where I give you some function, an oscillating function, and I just ask you to draw the phasor or to pick the phasor out of a set of choices for a particular time. So remember, this came up as we were developing the expressions for those RLC circuits where we did that vector addition with the phasors. The phasor is the y projection of the phasor is the magnitude of the function. So for example here, this value has a positive value because it's in positive y direction. So that tells me my phasor is either in the first or the second quadrant. And then I ask myself, well, is it increasing or decreasing? It's increasing, so that means I draw my phasor in the first quadrant. So make sure that you understand how we draw these phasors. They are kind of an important tool for other things. I think that's it. Oh, and then also transformers. You're likely to see a problem on transformers. Transformers, pretty straightforward. We went over them last time in class, so if you weren't here, you might want to look back at the screencast. Or if you look at old tests you'll see transformers. There's only one old test, I think, the last year's test where we actually did this. This is fairly new information, fairly new material for this class. But a transformer is an iron core. You have a primary coil like this. You have a secondary coil like this. This is my primary. This is my secondary. This is like what you have outside your house, where you have what is this? If I have a high voltage coming in, if I have a low voltage coming in, I get a high voltage coming out in this case. Is that right? No, I have a low voltage coming in, I get a high voltage coming out. Is that what I said? Yes. That is what I said, yes. Okay, so this would be a step up or step down transformer. This is a step up because I get a low voltage coming in, I get a high voltage coming out. I know that the voltage, my primary voltage, divided by the number of turns on the primary coil is equal to my secondary voltage divided by the number of turns on the secondary. So it's dependent upon the number of turns of wire. This is on your equation sheet, I think. Let me double check that. Let me clear all this, I'm sorry. Yeah, it's right here. So our primary voltage over our number of turns in our primary coil is our secondary divided by the number of turns on our secondary coil. So, for example, if I tell you that VP is 12 volts, NP is 4, VS is, we want to know, and NS is, say, 8, then I'm going to find that my secondary voltage is 24 volts. Just solving that. So I go from 12 volts to 24 volts. Those are fairly, I wouldn't say easy, but they're fairly easy, right? So you'll probably see that on the test. But it'll be a low point question, 5, 10 points, whatever. Okay? Any particular questions y'all want to go over? That's all the material we'll see for the test. It's a lot, and I know it seems a little overwhelming, especially these circuits that we've been doing are kind of funky. But focus on the homework, you'll be okay. And focus on the homework and then also on the examples we did in class. If you want to look at the old test, you can get a flavor of sort of how I'll change those things, but they'll be largely the same. Yeah?
If you look at that old test from last semester, how you don't have any like the multiple choice.
Oh, there are some multiple choice on this test, though.
But so they are going to have some stuff.
Yeah. I told them that wasn't a surprise for them. I think there are 10 multiple choice questions. We didn't have any clicker questions for Chapter 7 either. So, is that true? There are no Chapter 7 multiple choice? Yes, it is true. Okay? Cody? The general assessment will be on the day of the final. Our final is on the very last day. It's the Wednesday before grade review. So, okay. prepare for the final, you'll be prepared for the general education assessment, because this is cumulative, and your final's cumulative, so.
You have to finish the final.
Right, yeah, you'll have 20 minutes or whatever. Or if you can't do it on that particular time, we'll schedule it for that day, or the Tuesday before.
You got more support.
I don't know. Can I not say right now? I'm not sure. Probably like, did I say that right?
I think you already said that.
I already said that?
I heard you say
Yeah, I'm not inclined to make it worth 20. But you don't get it just if you take it, right? You get 20 if you make 100%. But some of you make 100%. Some of you make 80%. That's fine. Some of you make 50%. That's fine too. So, just do your, probably not make it. It'll be pretty easy. Okay?
Are we gonna have any of these concepts? That's chapter 7 concepts in the back of the book.
Oh yeah, but we didn't do them in class. I just forgot to do them.
So none of that's gonna be on there.
Well, the phasers will be on there. I already told you that. No, we didn't do I sort of talked about no, none of these are on there. On page 291 and 292. Yeah, no. I said, there is a phaser question, but you'll have a phaser question. I just say, what is the phaser? Like, draw the phaser, or pick out the phaser, what quadrant is the phaser in? Okay? 291, 292? No, because we didn't do them in class. All right? Other questions, though? And work through some stuff if you want. Yeah. Yeah. See how let's take a look at that. I could do it, Lazarus, but we're not going to have any circuits that are just inductors, just resistors, or just capacitors. And number 9 is that. So while it was useful, it was really only useful to deal with RLC circuits. Let me show you what I mean by that. Number 9, right? Yeah, so with that was number 8. Yeah, so number 8 and number 9, both of these are just R circuits or L circuits. So number 9 is a circuit that's hooked up to an inductor, and you're not going to see anything like that. You could see an RLC circuit though, or an LC circuit or an RL circuit, but not like number 9. Is that okay if I don't do it then? Is there another one? Any other homeworks? No, like I said, we were just sort of doing those to get up to RLC circuits. So at number 8 and number 9, it's really just number 8 and number 9. Not an easy one to look at, but you get the same by looking at number 12, number 11, number 10. Number 12, number 4, 5, 6, 7. Is that okay with you? Brandon?
Question. With the LC circuits on Wednesday, you drew the graph like 90 degrees out of phase, and today you drew it about 180.
Oh, did I? Yeah.
Are they completely out of phase, or are they, like, is it completely flipped from all voltage to no voltage, or current that is?
I may have misdrawn it. So for an LC circuit, that's when our energy goes back and forth. Let's see, so when my energy is at a maximum in one, it's at 0 in the other. Well, no, that's 90 degrees out of phase. So my energy, hold on, let me draw it. So when this is at a maximum, this is at, it's going to look like that, because when I have maximum energy here, I have 0 energy here. When I have maximum energy here, it has zero energy there. When I have zero energy here, I have maximum energy there. Let me double check that to be sure that's right. Yeah, that's right. When one is at its maximum, the other is zero. That energy trades back and forth, back and forth. Yeah, that's 90 degrees out of phase. 180 out of phase would be maximum.
Completely opposite, not considered flip, isn't it? Completely out of phase is considered flip. It's like,
Right. Yeah, these are completely out of phase. They're 90 degrees out of phase.
I was just thinking this 80 here completely.
I'm sorry.
I was wondering because it looked weird. Because they're going a few different ways and things have to reflect or something.
Right. And you might have to go up. If you go up, it's sorry. If I do it, I don't know what. Stop. There. Okay? Isolate tables. Everyone's know you break a plate, right? You know weight tables? Yeah. You break a plate and all the time. Those plates are expensive. Our manager used to always threaten us to dock everything, but he never did.
So when you see China on your paycheck, it doesn't mean you're on vacation.
Right, yeah. I used to be a bartender too, man. I still have nightmares about it. Break a glass. I never did this, but you break your glass and the ice in it, or done that?
Oh, no, so I got a really great glass.
Huh?
It melted all the ice.
It melts all the ice, they take up some hot water and melts all the ice. Yes. 12 people ask for stuff. Any particular questions that we can work through? Number 6. Let's take a look. Okay, yeah, number 6 is a good one. I mean, again, I think a good one. I don't know what's going to be on the test just yet, but I haven't finished making it out, but it's certainly worth looking at. Okay, number 6 is an LC circuit. It has an inductor. And on this, you need to realize that the energy of the magnetic field is 1/2 Li squared. Well, that's number 5, yes. Okay, I'm sorry. Number 5 is a good one, too. This is still an LC circuit, though. I still have a capacitor. I still have an inductor. So on this, you would look at your LC circuit, your LC circuits. You need to realize that your magnetic energy is equal to 1/2 Li squared, and your electric field energy, that's in the capacitor, is 1/2 Q squared over C. And if you want to find the current amplitude, that is, what is the maximum current in these oscillations, you set these two equal. So you say that my maximum magnetic energy is equal to my maximum electric field energy. So that's 1/2 Li squared equals 1/2 Q squared over C. All right, my energy trades back and forth, back and forth. And so I solved this for I. The halves cancel. It's going to be Q squared over CL, the square root of that. I can find Q because I have this capacitor, which is fully charged by this battery. So Q then is equal to C times V, or 6.2 times 34 volts. Which is 211 microcoulombs. And so I put that in over here. I would have 211 times 10 to the minus 6 squared over C, which is 6.2 times 10 to the minus 6. So my capacitance times L, which is 54, times 10 to the minus 3. I take the square root of all of that, and I get my current, which is going to be 0.36 amps. That's my maximum current when it's traveling through this circuit. Notice here that the way the circuit's set up, talk about in the problem that initially there was an A here and there was a B here. Initially the switch is to A. That's just to tell you that this 6.2 microfarad capacitor is fully charged by this 34 volt battery. So it's to tell you how much charge is on the capacitor. That's when I did that Q equals CV. And then it flips to position B, and it starts to oscillate back and forth between the capacitor and the inductor, the energy does. So this part is the answer for B, for part B. For part A, you want to know the frequency. Well, you want to know what F is. At what frequency does it oscillate back and forth? So you go to your equation sheet. Looking at LC circuits, which is what I'm dealing with, that's my omega, that's my angular frequency. So I'd say omega is equal to the square root of 1 over LC. That's the square root of 1 over 54 times 10 to the minus 3 times 6.2 times 10 to the minus 6. Square root of that, that is 1728. And then you say that, well, omega is equal to 2 pi f. So f is omega over 2 pi. And that works out to be 275 hertz. All right. So you need to realize that the energies were the way that we find our current. We did that in a homework problem. Well, this is a homework problem, actually. But so we did that in an example problem in class. We have to do this to find our maximum current, and then to find the frequency. It was how we found the solutions of that. It's given by our frequency. Just look at that equation. Okay. Homework's going to be key for this exam. Make sure you spend a lot of time on the homework. Do it blind. Stephen?
Do like a breakdown of how many true responses from the other two chapters.
I think there were 2 free response from chapter 5. And then the rest, 3 to 4, were from chapter 6 and 7. All right, you definitely have a Faraday's law, where the magnetic field is changing. You have to take the derivative of that function for B. We did a couple of those in class in the homework. So there's definitely a Faraday's law, and then also in that you need to apply Lenz's law to determine the direction of that. Y'all want to do one of those? Yeah. Listen, if y'all want to go, that's fine. I know y'all know their stuff. So if you got this, that's fine. But let's look. It's worthwhile to see this again. But I'm not offended if you go. But just to consider this a help session. I'm not offended really by much at all. Let's just look at number 1. Any one of these would be okay. Number 1, number 2, I think even number 3. Yeah, number 3, sort of. You have to find the flux. Well, let's look at number 1. So in number 1, I want to know the magnitude of the EMF that's induced. A couple things I need to do. First, I just recognize that E is equal to minus N d phi dt. All right, and so I'll need to find out what is phi, remembering that phi is equal to the magnetic field times the area. There's an integral involved in there, but since our dA is perpendicular, our area is perpendicular to our magnetic field, and our magnetic field doesn't change with the area, then we'll just say it's B times A, and that'll be the case for you. Okay, our first step is to find dB dt. dB dt is going to be 12t plus 7. Just took the derivative of this function. 2 times 6 is 12, t to the 2 minus 1, plus 1 times 7 is 7, t to the 1 minus 1. And I get this function. And then at t equal 2 seconds, this is equal to 24 plus 7, which is 31. So this is Tesla per second. The magnetic field is changing at 31 Tesla per second at t equal 2 seconds. That means the magnetic field, by the way, is increasing. I know it's increasing because, well, if I put in 3 seconds, it's going to be bigger, right? Because all these terms are positive, so the magnetic field is increasing. I also need to know my area. my area of this is pi r squared. I give the radius of the loop, so it's going to be pi times 0.015 meters squared, which is equal to 0.0007 square meters. All right, so that's my area. Now, I find E, n is equal to 1, so I'm just going to leave it off, is d phi dt, negative of d phi dt. That's going to be the negative of A dB, that is my flux, divided by dt. All right, and I work this out and I get 0.022 volts. All right, but now I also need to know what is the direction of this current, and that's where we go to Lenz's law. The magnetic field is into the page and increasing. So what is going to be the direction of the induced magnetic field?
Out of the page?
It's going to be out of the page, because Lenz's law talks about how our flux, our induced flux, wants to counteract the changing flux. So since this is increasing, the induced flux says, whoa, we got to hold back on what's going on. We want to stop what's happening. And so it's going to induce a magnetic field that is out of the page. So the induced magnetic field will be out of the page. This is V induced. And so then I ask myself, what current gives this induced magnetic field? Well, it would have to be a current that is going counterclockwise. Thumb in the direction of the current, fingers go into the page, out of the page. So my current here is in that direction. So I have a couple, my magnitude and the direction of the current. The direction is counterclockwise, and the magnitude is V over R from Ohm's law, 0.022, divided by, what was the resistance, 3 ohms, and that is what it is, it's 0.007. Remember Lenz's law, if this was decreasing, the magnetic field would be in the same direction as the magnetic field. Okay, so it would be into the page. You need to ask yourself the question, is this magnetic field, is it increasing or decreasing? You'll see a question very, very similar to this. Not identical to it, but similar. And it'll be worth 15 points. Okay? Anything else, Jeff? Particular questions?
I have a question.
What is it, Jeff?
How do you cut water?
Wow.
See, so
Oh, yeah. That's all right. Y'all didn't get my old, what was that joke that y'all didn't get? The Batman joke. And I was talking to my wife, I said, I don't think that y'all just have very good prowess in humor. That is a hella funny joke. Get in the car. That's a very funny joke. I told her it's just too sophisticated for y'all. Thanks, Shane. I'll write it down. That's a good one. Okay. Anything else, Joe? Okay. Well, we'll stop there then, if that's okay. I'm not too worried about the exam, but you got to know your homework to do well on it. So, know your homework. I can do that. If you don't yet, you have 2 days to do it. 7:15, we'll start the exam in here. I'll have a seating chart on the door.